Every night while users sleep, your system rebuilds the truth. Search results, recommendations, dashboards, fraud scores, they are often not created live. They are derived from yesterday's data.
That perfectly captures the reality of massive modern systems. When you interact with a major platform, it feels instant. It feels like it's reading your mind in real time. But behind the curtain, they don't calculate everything on the fly. Instead, they rely on an invisible, heavy-lifting factory processing massive amounts of historical data entirely behind the scenes. Today, we're going to tear down that curtain and look at the exact machinery inside.
We're going to break down exactly how raw data is transformed into product intelligence. We'll start with the concept of the factory itself, look back at its Unix blueprints, scale it up with MapReduce, tackle the immense challenge of distributed joins, and finally see how modern workflows power the features you use every single day.
Section 1. The Invisible Data Factory and Building Derived Data.
To kick things off, we need to understand why derived data even exists. When you build a typical web service, you're building an online system. It waits for a request, reacts, and responds as fast as possible. But batch processing is a completely different beast. Unlike online services reacting to immediate user requests, batch processing churns through what we call bounded datasets. That just means data of a known finite size. Think of yesterday's weblogs or a complete snapshot of a user database. The system takes this massive input, crunches it over minutes or even hours, and produces a brand new output. And crucially, it does this without ever modifying the original source data. It derives entirely new truths.
Section 2. Unix, the original blueprint, the plumbing analogy. Let's see how this builds from a concept you probably already use every day on your own terminal. If you've ever changed commands together in Linux, you've essentially built a miniature batch processing pipeline. Back in 1964, Doug McElroy, the inventor of Unix pipes, created this brilliant garden hose plumbing analogy. The big idea was to connect programs so that one program's output cleanly and directly becomes another's input. The inputs remain immutable, meaning they aren't destroyed or altered. Believe it or not, this simple, elegant philosophy perfectly models our massive, modern distributed data pipelines. It creates loose coupling, where each tool does one thing perfectly, and the data flows transparently from step to step.
Think about a really simple web server log analysis. Let's say you're trying to find the most popular URLs on your site. Standard Unix commands actually map exactly to the logic of distributed batch processing. A tool like awk acts as the mapper, extracting just the URLs from the raw logs. Then, the sort command acts as the shuffle and sort phase, grouping all those identical URLs together. Finally, unique acts as the reducer, counting the occurrences of each URL. It's the exact same mental model, just on a vastly different scale.
Section 3. Scaling up with MapReduce, moving processing to the data.
So, to scale this beyond a single machine's RAM and CPU limits, we need something far more powerful. We need distributed file systems like HDFS and computational frameworks like MapReduce. How does this scaling actually happen? Well, in traditional databases, you usually pull data over the network to your application code. But when you have petabytes of data, moving it over the network is disastrously slow. MapReduce flips this entirely on its head. It brilliantly schedules the map tasks to run on the very same physical machines that are already storing the data partitions. You are literally moving the computation to the data. This saves massive amounts of network bandwidth and allows thousands of machines to process logs entirely in parallel.
Now, what's really fascinating here is this term, the shuffle. It's incredibly counterintuitive. In everyday language, shuffling means mixing things up randomly, like a deck of cards. But in distributed systems, it is the exact opposite. The shuffle is a strict, highly organized phase where data is partitioned by the reducer it's destined for, sorted, and meticulously copied over the network. There is absolutely zero randomness here. It is the ultimate organizing mechanism of the whole batch factory.
Through these specific steps, MapReduce treats the extracted key, like our website URL from earlier, almost like a destination address on an envelope. During that shuffle phase, the system routes every single instance of the same URL to the exact same reducer machine. So, by the time the reducer actually starts running, it doesn't have to search around for data. All the identical keys are sitting right there, perfectly adjacent to one another, just waiting to be aggregated.
Section 4. The art of distributed joins, resolving associations at scale.
The real power of this invisible factory unlocks when we need to combine massive, distinct datasets. For example, imagine joining a massive fire hose of user clickstream logs with a static user profile database. Doing this at scale is incredibly tricky. You can't just have your batch job query a remote database for every single click. The network latency would completely destroy your throughput. So this is solved by something called a reduce-side sort-merge join. The mappers extract the user ID from both the click logs and the database snapshot. The shuffle routes them to the same reducer. But here is the truly genius part, the secondary sort. This guarantees that the reducer sees the user's profile record, like their date of birth, immediately before it processes their massive stream of clicks. The reducer just holds the profile in memory for a millisecond, processes all the clicks, and drops it. Absolutely no random network request required.
But there's a catch. Sorting and shuffling all that data is expensive, and this brings us to a major architectural decision. While reduce-side joins are incredibly flexible and handle whatever messy data you throw at them, they require immense sorting and copying over the network. On the flip side, if your data is already strictly partitioned and sorted, say from a previous nightly job, you can use map-side joins. These bypass the reducers entirely. The mapper just reads the identically partitioned files, merges them instantly, and outputs the result. It makes the whole process blazingly fast.
But what happens when the real world crashes into our perfectly organized system? Imagine a social network where one celebrity user suddenly generates 100 times more clicks than anyone else. Because the shuffle phase sends all data for one key to a single reducer, that one machine gets completely overwhelmed. This introduces a dangerous failure scenario known as data skew, or a hotspot. 99 reducers might finish their work in 5 minutes, but your entire massive batch job is forced to sit there and wait hours for that one stuck reducer to finish processing the celebrity's data. Handling this actually requires special sampling and randomization techniques just to break up the bottleneck.
Section 5. Evolving beyond MapReduce. The cost of intermediate state.
Despite MapReduce being the legendary algorithm that originally allowed Google to scale, it had severe architectural limitations that eventually forced the entire industry to evolve. First, the framework was notoriously rigid. Every single operation had to be forced into an alternating sequence of map, then reduce, map, then reduce. If you had a complex workflow of 10 jobs, job number 2 couldn't start a single task until job number 1 was 100% finished. But the most punishing bottleneck of all was what we call materialized intermediate state. Between every single MapReduce job, the framework forced the system to write the temporary data to the hard disk and replicate it across the network. It was incredibly safe and highly fault-tolerant, but horribly, painfully slow.
When we look at the evolution of these systems, we actually see a fascinating full circle. We started with Unix pipes in 1978, which smartly streamed data directly in memory from one process to the next. Then in 2004, MapReduce scaled this up but took a step backward in efficiency by forcing heavy, slow disk writes between every step for the sake of fault tolerance. Finally, modern dataflow engines like Spark and Flink came along and fixed this. They returned to the elegance of the Unix pipe philosophy. By analyzing the entire workflow up front, they skipped those unnecessary disk writes and passed data directly between operators in memory, maintaining scale while vastly increasing speed.
Section 6. Modern batch workflows. The final product.
So after all this immense computational heavy lifting, what does the invisible factory actually produce? Batch processing isn't just generating boring PDF reports for middle management. These workflows actually output the core components of your live production systems. They churn through documents to build immutable search indexes that are literally copied over to your live search servers. They analyze historical behavior to generate complex machine learning feature sets like real-time fraud scores, which are then bulk loaded into live read-only key value stores. They extract, transform, and load the raw events into structured data warehouses that power the analytics dashboards your teams look at every single morning.
So, what is the big takeaway here? It's that batch processing is not an outdated legacy system. Far from being some dinosaur of the Hadoop era, modern batch processing remains the essential, heavy-lifting foundation for data-intensive applications. It gracefully handles the immense volume and complexity that online, real-time systems simply cannot manage on their own. Ultimately, batch processing is not outdated. It is the invisible factory that turns raw data into product intelligence. But as stream processing continues to get faster and more capable, it leaves us with a fascinating architectural question. Will this invisible factory eventually operate entirely in real time, completely erasing the boundaries between batch and stream? Or will bounded historical data always remain the necessary bedrock for computing the ultimate truth? I hope this explainer helped you visualize the incredible machinery running behind the scenes. Keep designing, keep building, and I'll catch you in the next one.